begin with the algorithms for pass 1 of an assembler. Okay, this is the step 1. The pass 1 of an assembler, basically the first step happens to be breaking up each statement of your assembly program into tokens or pieces, that is separating the mnemonic opcode and the memory operands and the label, following which these steps can be followed, and the output would be generation of a symbol table if symbols are present in the assembly program, generation of a literal table if literals are present in the program, and you would also have a pull tab. Obviously, if there is literals, the literals are entered into our literal table, a pull tab has to be created, and we would generate an intermediate code which would then be used by our pass-2 assembler to generate the equivalent machine code. So our step 1, after we have separated the mnemonic opcodes, we have separated the memory operands and the label. First step happens to be initializing the location counter value to 0. Now location counter happens to hold the address of the next memory operand, right? Or it holds the address of the next instruction to be executed in the assembly program. So this location counter initial value is made 0, which happens to be the default value. Now this is our pull table, okay, which will contain how many literal pulls are there for that particular assembly program, and a pointer to this particular pull table will be represented by this variable pull tab underscore PTR. It is basically a pointer to this particular pull tab. Then you have a literal tab pointer which is set to 1, that is it will point to the first entry in the literal table, and pull tab will point to the first entry in the pull table. Now the step 2 is till you encounter end statement, that is till you reach the statement end, which signifies the end of the assembly program. These steps should be followed. First thing, you would check if a label is present in the statement. If there is a label present, you would copy that label into a temporary variable called this label, and would make the entry of that symbol that is present in this label and the location counter value into the symbol table. Now if it is an LTRG instruction, that is LTORG, that is literal organization statement, simply says that you have to associate address with the literals that you have encountered so far. So when you encounter an LTORG statement, you have to process all the literals that are present in the literal table for the current pull, and the current pull will be indicated by the entry in the pull tab. So you would allocate memory and put the addresses in the address field in the literal table with the associated literals. Then you would update your location counter accordingly. Now you will have to make the pointer point to the next entry into the pull tab, because a new pull has to be started. Okay, and similarly you would increment the pointer in the literal table so that you can make a new entry into the literal table if a literal is encountered in the program. Now if you encounter start or origin, basically these are statements indicating beginning of the program, then you will only take the value that is specified in the operand field and place it into the location counter variable. If you encounter an EQU statement, you will simply take the value that is present in the address space, copy it into a temporary variable called as this address, and you will, if you encounter an EQU statement, you will take the address that is present in the address space and will put it into a variable called as this address. Find the label corresponding that is occurs before the EQU keyword, and for that particular label you will associate the address. If it is a declaration statement, say if it is a DS or a DC, then you have to get the instruction code of that particular declaration statement. That is like mnemonic opcodes. You will also be getting codes for declaration statements. Okay. Then you have to see the size of the memory area occupied by DS or DC. That is how much memory is required to be allocated for the labels that are associated with these statements. Then you increment the location counter accordingly and generate an intermediate code. And if it is an imperative statement, you have to obtain the instruction code from the opcode table, okay, or a mnemonic opcode table. You will increment the location counter, okay, and then you will check if it is a literal. If it is a literal, you will make an entry into the literal table and increment the literal table pointer to point to the next entry. Or if it is not a literal, okay, you will have to simply take the entry number of the operand from the symbol table, place it into this entry and generate the intermediate code. It would obviously be a symbol. If it is not a literal, it obviously would be a symbol, and that symbol's entry can be taken from the symbol table and this intermediate code can be generated. Okay. When you get to your end statement, we have to perform step 2B, which is like processing the literals itself. That is this. So whatever you do when you encounter an LTORG statement, similarly when you encounter an end statement, that the same processing needs to be done. Okay, and then for the end statement you can generate an intermediate code, and then you will have to go to pass 2. We said in the algorithm, we said we generate an intermediate code. Now how is that intermediate code formed? Okay, now your intermediate code basically consists of units, and each unit will have 3 fields. Okay, so what are those 3 fields? It is an address, it is the representation of the mnemonic opcode, and representation of the operand. So if you look at this, okay, we have the address, okay, we have an opcode, and we have operands. This is basically 3 fields in one intermediate code. Now there are 2 variants, or there are 2 ways intermediate code can be written, and we have those 2 variant forms because we have to, as a system programmer, we need to make a choice between efficiency or execution speed and memory economy. That is, do you want to have efficient utilization of memory? If that is the case, we will have to use one form of intermediate code representation. Or do you want the processing of the assembly statement to go faster? Then in that case you will have to have an other variant form. So because you have to make a choice, there is always a trade-off between processing efficiency and memory economy. There are basically 2 variant forms. Okay. Now irrespective of the variant forms, okay, or you can say for the first variant form, okay, you can have the mnemonic field will contain a pair of this form, statement class and code. Now what is this statement class? Whether that mnemonic opcode that is present, does it belong to the imperative statement class, does it belong to the declarative statement class, or does it belong to the assembler directive class? Okay, now this code is basically, for an imperative statement it would be the instruction opcode itself, and for a declaration statement and assembly directives it would be the ordinal number within the class. So if you look here, declaration statement, there are 2 kinds, DC and DS. Ordinal number within the class specifies the entry into that particular table. Now this is a table that contains DC and DS, that is declaration statements. DC appears at entry 1, so the ordinal number of DC would be 1, and for DS it will be 2. Similarly, if you consider our assembly directives, you have start, end, origin, EQU and LTORG, and they are labeled from 1 to 5. So the ordinal number, say for example origin, would be 3. Now as an example, you can see this, okay, in variant 1, if I say start 200, now start happens to be an assembler directive, that is why we write AD, okay, comma, now within that assembler directive class, what is the ordinal number? So if you look here, start has the ordinal number 0, 1, and that is why we write here as 0, 1. Okay, that is for the mnemonic opcode. Now if you see read happens to be an imperative statement, and if you look through the mnemonic opcode table, we'll see that the instruction opcode of read happens to be 9. That is why we write IS, 09. Now if you look at move R, it is also an imperative statement, so we write IS, and its instruction opcode happens to be 4. That is where we write 04, and similarly for others.